There is room for more. If you have a project that you're working on that you could talk about for 15 minutes, I encourage you to sign up. So please take a look at the sign up sheet for that. That should be in your email. In just a few moments here, when Professor Zach Etienne gets online, he's going to begin his presentation. We have a 1.5 hours scheduled for him. However, there will be a break about halfway through. So, right. Does anybody have any questions before we begin?
All right, I could hear something. Hey, Steve.
Hey.
Yeah, sorry, I had a weird, unexpected technical glitch with
it happens.
Yep. All right, just a second. Let me get
even if your meeting's not in cyberspace, it can happen. Whenever you're ready, Zach, you can begin. Anyway, Dr. Zach Etienne is one of the more active contributors to the Einstein Toolkit. He has contributed a sizable number of thorns. He is a very active researcher in a number of gravitational physics areas. And he is here to show us his creation called NRPy, which is a Python interface to generating code for the Einstein Toolkit. Zach, start whenever you'd like.
Great, thanks, Steve. All right, so this is an interactive tutorial. I'd like everyone to go to nrpyplus.net, nrpyplus.net, as shown here. This is the easiest way to get to the NRPy tutorial. And when you press enter, you'll see it redirects you to my physics department website here. Just click on NRPy Plus tutorial on the left bar when you're ready. And you will see the top link here, the interactive NRPy Plus tutorial will appear. And click on that. And what it will do is it will load this cloud server. It will load an instance of NRPy on a cloud server hosted by mybinder.org, which is supported by multiple big names in cloud computing, including Google and a couple other big names. They donate their some of their spare CPU cycles to host mybinder. So it's a very, very nice community resource. And you'll see when it starts up, on the upper right, you'll see how much memory you're using as compared to how much you are allowed. I have not used any of these features up here, but they look pretty cool. Repos video chat, interesting. So this is a main NRPy, the NRPy main menu. And you'll see here many, many links. Each link is to its own Jupyter notebook. NRPy, as we'll see, has a very strict style guide that all NRPy notebooks, NRPy Jupyter notebooks have to abide by. So we are going to get started by clicking here, solving the scalar wave equation with NumPy. So click on that. And you'll see I have an author list. So something that you'll notice common to all NRPy Jupyter notebooks, there is some motivation at the top, the title, author list. The notebook status is important. It tells you, how much you can trust this notebook, whether it's in a very early experimental phase or whether it's fully validated. Validation notes are given as well, just to tell you what exactly the validation entailed. All NRPy Jupyter notebooks contain a table of contents, as you can see here, a clickable table of contents, where there's always a back to top option that will bring you back to the main table of contents. And you'll notice at the bottom of all NRPy Jupyter notebooks, there is a step where, provided you have PDF LaTeX, and I believe there's one other LaTeX related package you need installed, it will output for you, I forget the name, it will output for you this exact Jupyter notebook as a LaTeX PDF file, basically. So it's very nice. And I think, Steve, maybe you're unmuted right now. I could hear someone breathing.
Oh, I was muted. Someone else is. Let's see if I can find.
Okay. Great. All right. So what we're going to do as our first example, we're just going to use NumPy, which I think is a package many of us are familiar with. It is a numerical methods package in Python. It is used throughout data science these days. It may be the most popular package to use in the field of data science, certainly in the Python world. And since the Python world is the de facto center of the universe for data science, it is a very widely used thing. So you might, when taking a class on solving PDEs or computational physics, you might actually come across NumPy in your, and actually use NumPy in solving your homework assignments. So certainly a lot of my students have used NumPy. So I see this as, and Python, so I see this as a very nice introduction and motivation into NRPy. So just I like to always give credit where it's due. So this work was certainly not possible by the work of just myself. Other students, including Patrick Nelson, whose talk you'll hear after mine, Terrence's, whose talk you'll also hear after mine, Tiago, who is a new graduate student in my group as of last year, and so is Terrence, by the way. Leo Vernick, he is an incoming postdoc, but he's been using NRPy for about a year and a half at this point to do scalar field critical collapse calculations. And Brandon Clark, who was responsible for establishing the NRPy notebook formatting standards, from which you can get a nice, clean, uniform feel when you're in NRPy for all the notebooks. So the problem statement, we can go ahead and scroll it. You can see that the notebook status is validated, the validation notes. We've demonstrated that the numerical errors converge to the exact solution at the expected rate, and all that's documented below. All right, so prerequisites. In case you're new to the field, I have a lot of links on this page right here, online resources for numerical analysis and the basic mathematics behind this. So if you want to understand the output from your computer, you need to know scientific notation, and number of significant digits is very important. Some very basic mathematics and some links. All these are very nice vetted links that I've come across. Round off error, loss of significance. This is something very important that we all need to learn when we're doing numerical relativity. Linear algebra, function approximation, Fourier series. Some of these things are more useful than others. But the bottom line is we have a lot of links here, a lot of material that you can use. And really, you can't go wrong by looking at numerical recipes. It was written by numerical relativists. So I think it's a very, very good resource. It's one that it's a book that I regularly crack open. It's always on my desk. So that's step 0. And feel free, you can take this at your own pace. I'm gonna just sort of walk you through it. So this is an 1.5 hour long tutorial. What we'll do is we'll take a break at about the halfway point, 10-15 minute break, because it's really difficult, I find, to keep everyone focused, even my own focus for such an extended stretch. So
Zach.
Yeah, please.
Could I suggest that could you zoom in a bit? I think it would be better to see larger fonts and less of the screen. Even a little, yeah, that's better. All right, thanks.
There we go. All right. Thank you for the suggestion. Yeah. Good. So, so here's the scalar wave equation. It is sort of the model hyperbolic PDE, partial differential equation. It describes the motion of waves propagating in some uniform medium. And so the idea is we're going to write a Python code to numerically solve this equation. Now, let me just say that all this is to this introduction, perhaps the first half of this tutorial, is to sort of develop a common vocabulary. You're going to see terms used later on in the Einstein Toolkit notebooks, Einstein Toolkit Thorn notebooks, a lot of language that I'm going to develop here. So I sort of see this as a prerequisite understanding, and also understanding why I wrote NRPy in the first place. All right, so here's a scalar wave equation. We're going to solve it. You're given some set of initial conditions, that is U. So we're going to solve it in three spatial dimensions, X, Y, and Z, the Cartesian X, Y, and Z. And we're going to solve it. We're basically going to start with some initial data, initial condition, at t equals t naught, and then step it forward in time using a classical numerical technique. All right, so here's a mathematical problem statement. It's an initial value problem in Cartesian coordinates. The novel operator is just partial x squared plus partial y squared plus partial z squared, all acting on u. U is the amplitude of the wave. It's a function of space and time, or time and space, more appropriately. And c is the wave speed. We're going to assume c is a constant here. This is sort of standard. And the initial conditions given by this. We'll have suitable boundary conditions at the boundary. And what we're going to do, just for simplicity, is simply extrapolate the data on the outer boundary from the interior to the outer boundary of the grid. So we will find it quite useful to define v as the first time derivative of u, so that we can split up this second order PDE into a set of two coupled first order PDEs, where partial TU, of course, is this, but that's just v. And then partial TV is given by c squared Navier squared u, the Laplacian of u. So the idea is we're going to use NRPy to generate, ultimately we'll use NRPy to generate the C codes to do this, but as a first step, we're going to use just NumPy. All right, so our solution to the scalar wave equation, we're going to choose a what I call a spherical Gaussian solution. So it's a spherically symmetric solution. That is, you don't see, so you can write as a function of just r, the spherical coordinate r, which is just root x squared plus y squared plus z squared, and time. And so this consists of an outgoing wave, an ingoing wave, and we're going to add a constant offset to it as well. That's just going to be a constant. Okay. Now, obviously, what you'll notice is if you add a constant to u in this wave equation, so long as you originally satisfied the wave equation, adding a constant to it makes absolutely no difference. It still satisfies the wave equation perfectly. It will, of course, adjust the initial conditions, but we won't worry too much about that, because this will also serve as our initial condition. We'll just set t to some fiducial value. So C here is the wave speed. You can see this is a Gaussian distribution. In case you're not familiar, this is the most standard statistical distribution you'll find. I like it because it's extremely smooth. It's a very nice function. And you see there's an outgoing wave and there is an ingoing wave. And it's going to start at the origin. And what I'm going to do next is show off a little bit of the capabilities of SymPy, which is a symbolic algebra package akin to Mathematica or Maple. But this is, unlike Mathematica and Maple, a computer algebra system written in Python, and it is as open source as you can get, basically. It is BSD licensed, it is very permissively licensed, free for everyone. And because of that, I found it very compelling to use as the back-end computer algebra system for NRPy. And now we're going to demonstrate that this is indeed a solution to the scalar wave equation. So in Cartesian coordinates, we have that, and we know that R is that. So now we are going to just code it up. So here we have the independent variables. We're going to declare them as SymPy symbols. So here we imported SymPy as SP. Basically, this gives you access to the SymPy namespace as SP. So SP dot, and then any function that is in SymPy. So it allows for very nice code separation. So next we're going to declare the parameters C sigma, and I should also mention U offset as real valued symbols as well. Then we're going to define R, which of course is just the L2 norm of the 3 Cartesian components at a given point. Next, we're going to set up the solution. Now, normally I would have it at about yay font size, something like this, so I can see it all on the same screen. This is something I find very, very useful to developing in Jupyter Notebooks, developing code in Jupyter Notebooks. On the same screen, I can have the equation I'm trying to encode, namely this guy up here, U out, for example, and the expression typed up in Python below, all in the same field of view. So it's very easy to catch any potential errors that might arise. So first we have the outgoing wave, then we have the ingoing wave coded up, and then the exact solution just given by the sum of those. And then V, of course, is just the time derivative. Simply take the time derivative of U exact, and we have V. Great. So, oh man, really? You're gonna show, oh man. I thought my binder did this. That's okay. Hey, I think sorry about that. Just a second.
Zach, you could zoom in again.
I will, just a second. There we go, good. Yeah, so I've been blathering on long enough that my session with my binder has expired. And so I think it's 10 minutes. Okay, great. Okay, good. So it's now reloading this, but that's okay. So basically what I've done is I've pasted in a YouTube video, which should work, but I'm sorry it didn't. But basically what I want to show you is this is what the scalar wave, this Gaussian, there we go, looks like. So the colors here denote the solution, the exact solution of this wave equation. And up here you'll see the time, and this is x and z, so this is just in the xz plane. Remember, this is spherically symmetric, so if you pick a radius, the solution is going to be the same. The exact solution is going to be the same everywhere, regardless of what angle you choose. Okay, good. So let me get back into a live notebook. And you may have to do this as well. It may tell you that you've timed out. But normally when you have this loaded, you'll see the YouTube video embedded right here. For some reason, it's not working now. Whatever. Okay, so now we're going to confirm that that solution I claimed is a solution to the wave equation is in fact a solution. So what we're going to do is we're just going to take the right-hand side and subtract it from the left-hand side. Using SymPy to compute the second derivatives of U symbolically. And we're going to make it easy for SymPy to simplify. So this is a thing, this is when you pay $2,000 for a Mathematica license, the simplification algorithm is one of the main things you're paying for, I would argue. SymPy simplification algorithm sometimes needs a little bit of help. And by a little bit of help, here I'm going to take advantage of the fact that since a scalar wave equation is a linear PDE, each of the pieces, the ingoing wave, the outgoing wave, and the offset, should individually satisfy the wave equation. So what we'll do is we'll confirm that in fact, well, what we'll do is we'll subtract this, and subtract this, and then plug it in up here and just confirm everything is 0. So here it is. In fact, if you want, you can run all this, restart and run all cells. If you click here, it will run the entire notebook. And while you're waiting, go right here, and it should be able to evaluate this. Now, it does take a little while. Remember, NRPy is working very hard in the background. Its simplification algorithms will, there we go, right there, will in fact yield right-hand side minus left-hand side, or left-hand side minus right-hand side equals 0. It may take a little bit longer than Mathematica might take, for example. But it works beautifully. You can see we've confirmed that what we just typed in up here, U out, U in, ultimately U exact is in fact an exact solution. All right, so now when it comes to the initial condition, remember we're solving an initial value problem here. We're going to choose the above solution at t equals 0 as our initial data. And we're going to adopt what's known as the method of lines to advance the solution forward in time. So the thing is, I mentioned this in my classes before, the method of lines, thinking that there would be a nice literature on this. And my students could, just go open a book and find some information about this. But it turns out that it's actually kind of hard to find. So here I document the method of lines for this equation as completely as I could. So the idea is once we have initial condition, we want to, as we say in the numerical relativity community, evolve the initial data forward in time. In other words, just bring the solution to all the later time steps. We're going to do that using the method of lines. So here's the basic idea. It allows us to write the spatial derivatives. You can use whatever method you like. We're going to use standard finite difference approaches. You could also use pseudospectral methods. But here we're just going to use standard finite difference approaches to approximate the spatial derivatives. The temporal derivatives are going to be handled using standard strategies for solving ODEs. So long as the initial value problem can be written in this form. We have partial t f, some vector, in this case it's just u and v, is equal to some matrix acting on f, a matrix of operators. So the operator here is the Laplacian, and this is the scalar wave equation written in this matrix form. Now, very important, M cannot contain time explicitly or time derivatives. Although I think you could probably get away with a t, the more I think about it. I've never seen that though. All right, so the scalar wave equation is written like this, and it certainly satisfies that requirement, those requirements. So we're going to treat the spatial derivatives, like I said, using standard finite differences, and here's how it works. So let's say we have the RK4 method, right? So I hope we're all more or less familiar with this. This is something that you might learn in your differential equations class as an undergraduate, or it's distant relative, the Euler method for solving ODEs, initial value problems. So the idea is you have a standard ODE, y prime of t is equal to some function of y and t. Don't confuse this function with this function vector here. And so what you do is you evaluate these guys right here. So first you evaluate this right-hand side at the fiducial iteration n, so that could be 0, n could be 0. And then you follow through this pattern until you get to here, and then you can see that you're going to get y sub 1, the first iteration, is equal to the 0th iteration plus some linear combination of these k's, k1 through k4. So it's kind of interesting, actually. So Euler's method, we say RK4 because it's a quote-unquote fourth order method. Euler's method is known as a first order method, and it requires one evaluation of f for each step, going to yn plus 1 from yn. RK2, or Hoyne's method, or the Ralston method, all are various incarnations of RK2, requires 2 evaluations of this f function. And so you'll have yn plus 1 is equal to yn. There's a linear combination of k1 and k2. There's no k3 and k4. RK3 has 3. RK4 obviously has 4 k's. So here's a question. How much should RK6 have? And it just seems so obvious, right? Oh, it should have 6. But in fact, it has more than that. And it's been proven that for about higher than fourth order, this lovely pattern falls apart. And so you need more right-hand side evaluators. So RK4 is actually a very nice happy medium as a result of that, because F sometimes, as we know, can be very expensive to compute. For our case, our PDE involves two variables, U and V. And if you ever work this out in your ODE class for a system of two coupled ODEs, then this generalization will be exactly along the lines of what you expect. Now, things are a little bit different here, because when I say U and V, I'm referring to what we call grid functions, okay? So U is defined at all points in space, X, Y, Z, on your numerical domain, and so is V. So K, in fact, is not just like when we were solving a simple ODE of one independent variable. It's not like these are scalars. Here, these are actually three-dimensional objects that we call them grid functions, because they sample our numerical solution or some variation of that at every point in our numerical domain, excluding the ghost zones on the outer boundary. But that's a story for the next section. All right, so K1U is V, right? So this is F. So we're going to have basically what happens is K1 gets split into two pieces because we have two coupled PDEs in this case. If we had two coupled ODEs, it would be the same pattern. Now notice that what we have here, K1 is equal to, K1U is equal to Vn, right? Because that is the F on the right-hand side of U, right? So this is U is equal to V. Partial TU, I mean, is equal to V. And so that's why we have V here. K1V is just C squared nabla squared U. Again, we're just following this approach right here. And then K2, you'll see, as it depended in the ordinary RK4, depends on K1. And what you must do then to generate K2 is you must evaluate K1 first, storing the solution at all grid points, including the outer boundary. So basically, after evaluating K1, you have to evaluate the data on the outer boundary. So what I do and what we'll do is we'll actually perform this sum, and then we'll apply the boundary condition, and then we will evaluate K2 U and K2V. And then we'll move on to K3, which depends on K2, which depends on K1. So you see, this order is fixed. K4 depends on K3, depends on K2. So UN plus 1 depends on all the Ks. K4 depends on K3. K3 depends on K2. K2 depends on K1. So you can't do this out of order. It's very strict. And you notice here that we have something kind of weird on the right-hand side, something that you wouldn't see if you were just solving a simple ODE. We see a spatial derivative, a nabla squared U. What we're going to do is, remember, all these are in 3 dimensions. So what we're going to do is actually take a finite difference derivative of U at the, let's say, the initial time, n equals 0. And we're going to perform, this algorithm. And then at the end of the day, we're going to get the U and V at the next iteration. And there's another interesting story to be told here. This, in fact, is true. We say it's RK4, in other words, it's 4th order accurate, yet according to this, after one step, the error is to the 5th power on the time step delta t. I'll let you think about why that might be. The answer is a little bit subtle, but let's keep moving. All right, so again, the idea is we're given initial data U at times iteration 0, V at iteration 0, n equals 0. We can get U at iteration 1 and V at iteration 1 by just applying this straightforward approach. All right, so let's go to our implementation of this. Now that we have sort of basic idea what method of lines is, let's talk a little bit about the basic algorithm that we're going to implement in pure NumPy. So we're going to do just a couple of important definitions. The notion of a grid function. Remember, that's just a numerical solution at a given instant in time on a 3-dimensional numerical grid is a grid function, okay? that is, we're going to have one for U, one for V. And it turns out we're going to need a lot of temporaries for the Ks as we go along. It is possible to make it more efficient, and actually I should add that as a exercise to the student. All right, so first we're going to set up our numerical grid and the free parameters. Then we're going to allocate memory for the grid functions, including all the temporary storage. We're going to set grid function values to the initial data, and then we're going to step the system forward in time using this algorithm right here I just outlined. And at each RK substep, we have to evaluate the right-hand sides, which are these guys on the right-hand side, appropriately enough, of these Ks. And then we're going to have to apply boundary conditions, because if you think about it, when you take a finite difference derivative of U that's centered, you are only going to be able to evaluate that on the interior of the grid, where that finite difference stencil reaches beyond the outer boundary. You can no longer update this expression. So what we'll do is we'll apply boundary conditions to fill those data in. Okay. And there's also a diagnostic that will output as well. Okay, so we're next going to set up the numerical grid and free parameters as promised. So what we're going to do is we're going to choose a cell-centered grid. So you'll notice that near the origin, we do not include xi. So, okay, let me see here. Coordinate points in x, y, and z directions respectively. They're going to have nx by ny by nz. So this is a rectangular prism in general of a numerical domain. The grid's uniform, so we can describe the x coordinate of any grid point with a single integer I, and the same holds true for y and z, which will use integers j and k respectively. So we'll label each grid point x sub I, y sub j, and z sub k. We're going to choose a cell-centered grid that avoids the origin. Now we want to avoid the origin because you'll notice in our initial condition that we're dividing by r. Now, if our numerical code, well, if finite difference arithmetic were smarter, we wouldn't have to worry about this, because really it's just at time 0, it's just r divided by r, 0 divided by 0. But we would first take the limit and do this appropriately if we were doing this by hand. But unfortunately, we don't have that ability. So what we'll do is instead just choose a numerical grid that never samples the r equals 0 point. So that's why we're avoiding r equals 0 here. There are certain tricks that you can apply, and I think the usual approach in other Einstein toolkit thorns is to instead apply one of those special tricks. But here we're just going to apply this trick. All right, so if you look at how this is set up, the general expression is given by the minimum value of x of your domain, and plus I minus the number of ghost zones. We're going to be using fourth order finite differences, and we'll go over that very soon. And we'll see that the number of ghost zones associated with that is 2. The stencil width is a total of 5 points, including the center. And so the number of ghost zones is 2 from any grid point where we're evaluating the derivative. All right, so delta x is the spacing between grid points, and delta x is given by x max minus x min divided by nx. And what we're going to do is we're just going to make this very simple. We're going to choose a numerical grid that is a cube with a domain size of 10. X min is minus domain size, x max is plus domain size, y min is also minus domain size, etc. So delta x equals delta y equals delta z equals this. X minus max x min minus divided by nx. All right, so now we're going to start writing the code. Based on what we've developed here, we're going to set up the numerical grid. The domain size we're going to set to 1, which is a very, very boring thing. Unfortunately, this code, as we'll see, is so slow that we can't do very much very interesting with it. If we reduce the dimensionality, it would run a lot faster. We might be able to do more interesting things with it. But again, the point here is to motivate the use of NRPy and motivate the use of, well, motivate us to get out of the pure Python coding mindset and into something that is going to perform reasonably well. Not just for the scale wave equation, but for goodness sake, Einstein's equations of general relativity, which are far, far more computationally costly. So again, what I normally do is I would have it zoomed out to about here so I could see the equations as I'm typing them in. And you notice one thing I like to do is line up things. So I see I, J, K, X, Y, Z, X, Y, Z, I, J, K. I like this lining up, and sometimes it requires adding extra spaces that Python coding standards don't necessarily like, but you know, we're trying to minimize human error. We're not trying to appease the Python gods. So we're going to use some simple NumPy functions. First, we're going to declare these as one-dimensional arrays, XX, YY, and ZZ. And we're using XX, YY, ZZ because up here we defined X, Y, and Z to be SymPy variables. So that's what we're doing. And so these are just simple 1D NumPy arrays. Next, we're going to set the free parameters for the scalar wave solution. We're going to set C to 1, which is pretty standard in our field. Free param sigma, this is the width of the Gaussian, we're going to set to 3. And the offset, we're going to set to 1. It will be an exercise to the student at the bottom. What does it mean? Why did we choose a non-zero offset here? And the answer is, requires a little bit of thought. Okay, next we're going to set the time step. So when you solve PDE numerically, there's this so-called CFL condition, the Courant-Friedrichs-Levy condition. And you'll notice one great thing about Jupyter Notebooks is you can just include links to exactly what it is you're talking about. So if anyone's confused, you know, you're not like just reading pure code and someone pastes in this. You can just click and then go back when you're satisfied you understand what it is that was just uttered. Okay. So we're going to set our CFL condition. We're going to choose our CFL condition to have our CFL factor to be 0.5 here. And to have proper units, you have to have, so we're looking at the minimum between x, dx, dy, and dz, and you have to divide by the wave speed in order for this to be proper units. And we're going to set the final time to half the domain size. So what we're going to do is in our actual code that where we solve this equation, we're going to output the data at the origin. That just also, it's a convenient place because it happens to be the point that's farthest from the outer boundary. Because our outer boundary conditions, as we'll see, are very crude and approximate, what you will find, spoiler alert, is that if you continue the simulation, let's say instead of 0.5 to 1.5 or 2.5, that the approximation, the outer boundary approximation will start to dominate the numerical error. That is because we're choosing a very crude outer boundary condition. And in numerical relativity, we do not have excellent boundary conditions for our numerical relativity simulations. So the usual trick is to choose something like an outgoing wave boundary condition, also known as a Sommerfeld or radiation boundary condition, and couple that to grids, grids with outer boundaries very, very far away. That we're able to do that, for example, with carpet, which allows us to choose coarser and coarser AMR grids, such that we can push that outer boundary extremely far away. Basically, you could even choose the outer boundary to be out of causal contact from the interior region of your grid, where you're, say, modeling the orbits of two black holes and measuring the gravitational waves, maybe 100 times that orbital separation away, and then you just push the outer boundary to 1,000 times that or something. 1,000 times that, 10 or 20 times that. And you'll see that it behaves quite well, even though your outer boundary conditions are very approximate. All right, so NumPy implementation, we're going to next set up the initial data. So remember, this is the initial data that we're choosing, the spherical Gaussian. And what I'm going to do here is a little bit hackish. The first thing I did was I just used SymPy, and I replaced all the SymPy variables R, T, and what have you with the actual values at the coordinate locations. The problem is that was excruciatingly slow. So what I did instead was output this as a string, the SymPy expression as a string, and just did some string manipulation. This is really hacky. It's not something that you would ever do in NRPy, that's for sure. But it's just something I did to make this code run fast enough to where I'm not pulling out all my hair. So that's basically what I did. There was also some by hand optimizations as well. But you can see it's kind of an ugly expression, both of them. But they are the correct exact solution. Again, we're just going to use this for setting up initial data and for comparing our numerical value, measuring the error of our numerical solution as compared to the exact solution. So here we create a loop for given the exact solution at all points. And I wrote this in a somewhat optimized way. Something very important, I don't know, how could I skip that over? Did I skip that over? I must have skipped it over, sorry. There is, you notice here that there's this IDX3D. This is a function in Python. Okay, I'm missing the first one somewhere. Anyway, IDX3D basically allows you to declare, instead of declaring a 3-dimensional array in NumPy, we instead declare, hey, look, it showed up on this version. That's weird. Okay, anyway. IDX3D allows us to map a 1-dimensional array. I guess here it is. It's declared down here. That's right. Yeah, sorry. So this is done in the Einstein toolkit extensively, and also it's done in native NRPy codes. So instead of declaring a multidimensional array, like a 3D array, which are pains in the butt and not well supported by every language, certainly not consistently supported by different languages, we're instead going to declare U and V as 1-dimensional arrays, each with the requisite number of grid points that you would need to store the 3 dimensions of data. And so to access an arbitrary point, you're just going to call this simple function. It's going to be a function of ijk, and basically what it's going to return is something this, which if you do the math is the correct function, basically. And so this is the function itself that you saw there. I should probably move that up a little bit higher. But here's the function that you see, and we're going to basically compute the exact solution at a single point, looping over all grid points in all 3 dimensions. All right, so next we're going to allocate the memory for the grid functions. Remember that we want nx by ny by nz points in our grid interior, but we're going to need ghost zones on the positive face of that cube and the negative face of that cube for all 6 faces, basically. So that means we need nx plus 2 n ghosts in points in the x direction, ny plus 2 n ghosts in the y direction, and nz plus 2 n ghosts in the z direction. So we're just going to initialize those to zeros. And by the way, when someone says poisoning, mentions the term poisoning, that just means instead of setting these to zeros, you set them to a floating point value, like not a number or infinity. And that way you know whether you have a data dependency issue somewhere in your code. Okay, so next we're going to define the right-hand sides, which need to be evaluated, of course, with our method of lines approach. And what we're going to do is we're going to approximate this nabla operator with 4th order finite difference derivatives. There's a NRPy tutorial notebook on how to compute these expressions automatically. And here it is, just to show you. Where basically we construct a matrix equation. Oops. There is a NRPy interface for computing arbitrary finite difference stencils. But we're just going to use a Wikipedia article on finite difference coefficients, which is a very nice little reference right here. And by the way, one of the validation tests that we do in the NRPy notebook is actually reproduce this table. Exactly. So here it is. Here's a 4th order finite difference stencil for the x component. Of course, we'll need y and z as well, but I'm just going to group these coefficients because you see a 4/3 happens twice, a 1/12 happens twice, and a 5/2 happens once. So we're just going to group those. And this is how we evaluate the right-hand side. So u right-hand side, remember, is just v, right, given right here. And v right-hand side is given by c squared, nabla squared u. So we're going to add up first the x term, and then the y component of nabla, and then, oh, that's kind of silly, the z component of nabla. There we go. And you see that we're keeping all other coordinates fixed. We're just looping over i's, which represent the x direction, j's, which represent y, and k's, which represent z. All right, now the boundary conditions, okay? So what we're going to do is we're going to apply quadratic extrapolation. So we're just going to, if you know about Lagrange polynomial interpolation, well, this is just using the same basic approach, but to extrapolate. It is the cause, Lagrange polynomial extrapolation is the cause of countless some billions and trillions of dollars lost in the stock market because people think that past performance will indicate future gains. And they just use a polynomial extrapolation to, it's called technical analysis. Yes.
Yeah. Hey, Zach.
Yeah, sorry.
This is right about your halfway mark.
Thank you, thank you. And I'm getting very close.
Okay.
How about we could do 5 more minutes and then we'll take a break, okay? All right, so the boundary conditions, and here I have an animation showing off. So I do this using a particular looping structure. And Leo Vernick actually created this very nice animation to show exactly what this loop structure is doing, at least in 2 dimensions. And you can see what it does. It first fills in the X point, minimum, face maximum, and then the Y minimum, maximum, and just continues looping through. You can see the green points getting filled as it goes. I guess it's doing here the Y direction first. Doesn't matter. So that's basically how that works. The method of lines, we've already gone through that. What we're going to do is we're going to declare grid functions for all these Ks, and also something just to keep track of what goes into these F functions. Okay, so we're going to have a couple of temp variables and then one for each of the Ks for each of the grid functions U and V. And then here is the our case step where we evaluate the right-hand side. And then we compute the inputs into K2, which you can see right here should be 1/2 delta TK1. Here it is, 1/2 delta TK1 plus the input value yn. So this could be the initial data, for example. And that's true for U and V. And then we're going to apply the extrapolation boundary conditions on what is going to go into this function F for K2. And then we evaluate the right-hand sides again. Basically, we're going to evaluate now this right-hand side right here for K2. And then we're going to compute the inputs into K3, and we're going to move on. And then we do the same thing for K4. And then the main driver function, we'll get into that after the break. So I will pause here. Let's take some minutes break, and I will also take a little break myself. Shall we reconvene in how long? 10 minutes?
Let's start at 10.
Okay, great. We'll start at the top of the hour. All right, so hope everyone had a nice break. Yeah, I realize now that to get the YouTube video to appear, you actually have to evaluate this cell. So to evaluate a cell in a Jupyter Notebook is just a matter of clicking inside it and pressing Shift Enter, or clicking this Run button here, putting your cursor inside there, and then clicking Run, and that will do it for you. Sorry. All right, so basically I zoomed out again. I just wanted to show that here's normally how I would develop the code at about this font size. It's not for everyone, but it does the trick. So you see K1, K4, YN plus 1. You can see everything appearing up here in the LaTeX expression, appearing down here in the code very nicely. Let me get the font size back up to something that's friendlier. Here we go. Okay, so then we have the main driver function, which is going to set the initial time. I have this is called a interactive Python or IPython magic command. What it does is when you put this at the top of a cell, it will actually time how long it took to run this cell, which is kind of an important consideration when you're optimizing Python code. Or even optimizing any code that's running within a cell. It could be C code even. So we have initial time, we're going to set to 0, like I said before. We're going to set up the initial data, which is just the exact solution at all points at the initial time with inputs, grid functions U and V. And this function was defined up there. You can scroll up and see it, look at it if you want. What we're going to do is we're going to have a diagnostic. We're going to store the index at the point closest to the origin. And that's just the total number of grid points divided by 2 in I, J, and K directions. Because our grid is centered on the origin, after all, but there is not a grid point at the origin. It's just the numerical domain is centered at the origin. And our diagnostic is just going to consist of computing the log base 10 of the relative error between numerical and exact solutions. And that's how that works. And we're going to output first diagnostic at the initial time, and then we're going to set up our final iteration, how often we want to output, and that depends on our resolution. Our fiducial resolution is going to be 24 cubed. We'll do 24 cubed, 48 cubed, and 96 cubed. 48 and 96 take a long time, and I've pre-computed those results and pasted them below so you don't have to wait. And so basically what happens is when you run this, all right, so first of all, your Jupyter notebook, your My Binder is probably dead at this point if you've been idle for more than 10 minutes. So what you want to do is go to the chat. You think so? The other computer is closed, actually, I think. Yeah, sorry, someone sent me a message saying that I have a mic open. Let me go ahead and mute that if it's not already muted. Okay, I think that's better. All right, sorry about that. Gee whiz. It seemed like the mic loved to work, but the speakers didn't. Okay, all right, so so what I did here was I wrote a little thing, a little benchmarking thing that you can implement in C, and in fact I do implement it in C because sometimes solving Einstein's equations can take a long time, and I want to know how much longer, basically how long will my coffee break be? And so the idea is if you are, if you're tuned into chat, I'm going to paste in the link again for the interactive tutorial if you'd like to do this yourself. Basically, you can relaunch this. What I'm going to do is I'm going to restart and run all cells, which is just this fast forward button here, and then you click restart and run all cells, the red button. And what we're going to do is we're going to see, so first it's going to do that simplification up here, which takes maybe 10 seconds. And then it's going to continue on and generate this lovely Python code. Okay, good, we're already past that. And now watch, it tells you how much longer it's going to take. How cool is that? So it started out about 12 seconds. We're down to 5. It's almost like we're launching a space shuttle here. Great. So it integrated, and here are the results that it generated. It also output these results to a file. I call it output experiment at resolution something cubed. But what I did was I ran this notebook at 3 different resolutions, 24 cubed, 48, and 96 cubed. And you'll notice the code is slow. And let me just point out that it's ridiculously slow. It takes 16 seconds to complete roughly, and you can see the time for this entire code cell took about 15.2 seconds. So if you double the resolution to 48 cubed, the domain size, fix the number of grid points, increases by a factor of 8, and the time step reduces by a factor of 2. That's the CFL criterion. So the total cost is about 16 times higher. So 16 times 16, about 4 minutes to compute the solution for 48 cubed. And for 96 cubed, oh boy, that 16, extra factor of 16 really hurts. And about over an hour to complete a simulation. And I don't think that Binder will let you do a run for over an hour. So this is one reason we like to use NRPy Plus. We want to convert these a human-friendly Python code into something that's highly optimized and written in C. And we'll see in the next notebook that we'll navigate that the results are about 10,000 times faster if you run it in C instead. So this is how we can do science in numerical relativity. If we were completely reliant on just the Python language and NumPy, the field would be 50 years, as it was 50 years ago, basically. So lots happened in CPU infrastructure, and luckily we don't have to use pure Python to do these things. So it's not just the fact that NRPy generates codes that are much faster, that are written in C. There are also a number of other very nice advantages to NRPy. It contains a rigid syntax for SymPy symbols that lets you specify derivatives and output C-coded arbitrary finite differencing order. So for example, I could say, okay, now let's redo the above code, but let's instead do it at 6th order finite differencing and use RK6. Well, that would require an extensive rewrite and something that can be very painstaking and to get right and debug. So each of these links, I should point out, this is another advantage of NRPy, is it's extensively documented. Each of these links is its own NRPy tutorial Jupyter notebook. So for example, just clicking on a random one, validating RK expressions that we coded up in NRPy. So NRPy contains a dictionary of Python dictionary of Runge-Kutta butcher tables. And what we do here is actually solve a number of ODEs with those butcher tables and confirm that in fact we get the order that we expect in the result. So that in fact the RK method is the order that we expect. And it's all described here, how that's done. So that's just one small example. There are 2 boundary condition drivers. There's a generic one that by default uses the same quadratic extrapolation boundary condition. Terrence, who will be giving a talk very soon, has actually done a lot of work on implementing the Sommerfeld boundary conditions, which is kind of a clone of what NuRAD does. And NRPy provides support for solving this equation stably in curvilinear coordinates, and even, of course, Cartesian, spherical-like, cylindrical-like, prolate spheroidal-like coordinates, you name it, it supports those. So let's see. I wanted to go next to, let me see if this is the right one. It's just generating the C code. All right, so let's go back to the main menu. We're going to scroll down to a scalar wave equation. There's a start to finish example, which is numerically solving the scalar wave equation, a complete C code. And I'll see if I can paste that into the chat in case you want to access this directly. We're not going to spend a lot of time on this. but I just wanted to, come on. Select all, paste, no, copy, okay, there we go. All right. Okay, there you go. If you want to access this directly, there it is, the start to finish Cartesian modules, which does exactly the same thing, almost. I mean, there are a couple of things like I let the simulation go, the domain size is 10 in this case. It actually does something interesting. The run goes to, I think, 0.8 or 0.7. There we go, yep. T final is the domain size times 0.8 basically in this case. So it goes for a bit longer. And if you run this, what it will do is it will use NRPy to generate the necessary C code kernels, which are documented in other notebooks here. And at the bottom, you can see here it just did a 96 cubed resolution to, so remember the other one did it to 0.5 times the domain size. This did it to 0.8 times that in 3.4 seconds. Compare that to over an hour, and you'll see that that is a very, very significant speed up. And this, by the way, is only using one core on this computer. If you use multiple cores, it can speed up by multiple factors beyond that, because this, what NRPy generates is fully OpenMP capable code, C code. So basically what you do is instead of writing a full Python code, you instead teach NRPy what you want to do. So we have domain size of 10, RK method we set to RK4, we set the finite differencing order to 4 right here. We import the scalar wave initial data notebook, which actually Python module, which is extensively documented in a Python note, in a Jupyter notebook. The right-hand side module, our grid dimensions 3. We're going to choose plane wave. We can also change this to spherical Gaussian, which is what we just did in the pure Python version, the NumPy version. Here we set up the scalar wave right-hand sides, the C expressions, sorry, the SymPy expressions. And here we use NRPy's low-level FD output C routine, which outputs a C code kernel with finite differencing. The exact finite differencing order you specified right here is set when you use this output C right here. So this is the function to evaluate scalar wave right-hand sides. This is a very neat little Python function that I wrote that outputs a C code function. So this function is RHS eval. Here are the input parameters. Here is what goes in the body equals. And you can also specify loop options. So basically by default, if you will, you can assume that there is a loop inside the body, and the loop is going to be over interior points, and we're going to enable single instruction multiple data intrinsics. And if you want to see what this looks like, oh, I see, okay. What the code looks like, either you can run that and then look at the output, or you can just look at this. So for example, if we did this is just a 1D scalar wave equation. This is not using SIMD, but we can go down here. Here's an SIMD example for 3D with 10th order finite difference stencils. Again, you can choose whatever even number you like here, so long as it's greater than 0. And you can see it's actually reading using these C macros, which are macros to SIMD intrinsics. If this sounds complicated to you, the bottom line is what this allows you to do is evaluate multiple grid points in each CPU cycle. If you have a modern CPU, then it will allow you to update 4 grid points at once in double precision. If you have an exotic, very recent, certain Intel chip, you can do 8 at once, but the speed up isn't quite double that of 4. So anyway, you can run this if you like, again, and it only takes a few seconds to run the whole thing. So it actually ran it in 48, 64, and 96 cube resolution. And here we show the convergence. So this is something that I sort of skipped over in my previous one. The error analysis, which is very important, actually pre-computed, again, the 24 cube, 48 cube, and 96 cube results. Here is a description of how you do a standard error analysis in numerical relativity or in general numerical analysis. So basically, when you double the resolution, if you're taking the log base 10 of the relative error, the error should drop by 1.2 on a logarithmic plot. And then when you quadruple the resolution, it's 2.4 naturally. And so basically what I did was I plotted this, assuming that these logarithmic drops are as they should be, and we should see a perfect overlap between the three resolutions. And we do, except at time 0, where we're not dominated by this truncation error, the error in our finite differencing or time stepping, but instead the initial condition, which is known to 16 significant digits. So there's some exercises to students down here if you like. You can output this notebook to a LaTeX formatted PDF if, in fact, you have the PDF LaTeX installed, which is not installed on here, but it's something you can work out for yourself. Okay, so at the bottom of this notebook, we demonstrate fourth order convergence, just like we did in the other notebook. And that's going 64, just looking at 64 versus 48. In this one, of course, we looked at 3 different resolutions and they all overlap very beautifully. All right, so now we're on to the very last bit. So we only have about 7 more minutes. We're going to go over ID scalar wave NRPy. So this is writing 2 Einstein toolkit thorns for solving the scalar wave equation. So first, let's look at the ID scalar wave NRPy. Again, I'm just going from the main table of contents here of NRPy. So I have to give special thanks to Patrick Nelson, whose name I forgot to put on here, Terence Pierre-Jacques, who modernized this infrastructure, these thorns. After about a year of development of NRPy, a lot of internals have been automated and done better. And so Terence updated this to a more modern version of NRPy. And basically what this does is it constructs Einstein toolkit thorn for setting up the scalar wave initial data using NRPy. So what we do is we add some options, whether you want to do plane wave or spherical Gaussian. And I believe this will output both as options in your runtime options. So either you choose, so a plane wave is just a monochromatic wave that propagates in one direction along your grid. I think it's along the diagonal, XYZ diagonal. Spherical Gaussian is exactly as I described before. We register grid functions in NRPy, which do exist in the toolkit. X, Y, and Z are grid functions in the toolkit. We're also going to register some grid functions specific to this thorn, or specific actually to the wave toy NRPy thorn, U, U, and VV, to represent the solution and its time derivative. Here we set up the symbolic expressions, the C code kernel, which takes in these symbolic expressions and converts them to highly optimized C code. And here's the main loop. This is a manual way of doing loops. We have more automated ways of doing this, but this is very good still. You can see it's just a simple, it just generates a simple C loop structure. Again, this is also documented in a loop Jupyter notebook, if you like. Write the C code kernel to a file, which is just scalar wave and then whatever initial data you want. And in fact, it loops over the 2 different options, plane wave and spherical Gaussian, and outputs 2 header files, which are then pulled in by the rest. So first the CCL files, interface at CCL. This is just using a template. We're not actually outputting any grid functions for this thorn because it's just an initial data thorn. It's going to depend on wave toy NRPy, as you can see here. which does actually declare the good functions. And here we have an automated param.ccl generation interface, which sets up your parameters. And actually there's a link here to the official Einstein Toolkit documentation to learn more about what param.ccl does. This is all rather automated. There's not a lot you need to modify, maybe a little bit right here, just to indicate what it shares. Einstein Toolkit thorns, the other Einstein Toolkit thorn and thorns, I guess. So it depends on grid and wave-toy NRPy's wave speed parameter. Initial data type is automatically generated here. All right, schedule.ccl. So this is just based off of what already exists in the toolkit. There are multiple wave-toy codes, so this is just a template. We do want to generalize this and add reads and writes to this, which will not be a very difficult thing once we teach NRPy about these functions it's creating. And that is an in-progress thing. We just started our new Einstein Toolkit grant, and that is one of the goals of the grant. So stay tuned, it will be there soon. I have a little function here that appends the C files as we create them to this make code definition, which is kind of like a make file, sort of, for Einstein Toolkit thorns. And it basically appends it as you write to it. So we're writing to initialdata.c. Here is the basic code, and we're including the files that we just generated, the C code functions that we just generated into the C code. And then we write finally the make code definition. This is just kind of a standard thing. And finally, we output this to a LaTeX PDF file. All right, finally, wave-toy NRPy, which is a little bit more complicated, but it's all pretty well documented again. So you set up your ETK directory for various Python files. So this is written very similarly to how by call is written. The issue with by call is because we generate the BSSN, the Einstein's equations and the BSSN formulation in multiple finite differencing orders, if you were to generate all the codes by call is comprised of, in serial, it would take a very long time. So what we do here is, instead of just running the Python code directly from the Jupyter Notebook, we instead write it to the subdirectory. And then we call these functions from a multi-processing context. So we can actually generate the C code kernels in parallel. And I'll show you what that means. I'm going to run it now. This is something you can't do in Mathematica, by the way. Oh, wow, that was quick. Let me see, where did it generate the code? Here we go. Generate the code in parallel if possible. You see, so it ran this super fast, okay? It did everything in about 4 seconds. It used up all the CPU cores that were available on this cloud server that we're on. And it generated the right-hand sides for the scalar wave equation, second, fourth, sixth, and eighth orders, all simultaneously, all at once. And then it output everything. So there's a little bit of complication involved with this multi-processing thing. You basically have to create a separate NRPy instance, and this is just keeping track of the NRPy environments. This is actually going to be moved out to a separate NRPy low-level code. But that just shows you what is there. And again, we're using this automated param.ccl generator that's using the parameters that you specified, you registered with NRPy, but in the param.ccl. There's a little bit of hand coding here. We don't support like multiple options for parameters. So this is how this is done right here. Slightly clunky right now, but it is in progress to make it much more elegant. The interface.ccl does in fact use the list of grid functions that you declared. You need a few other things like the new rad, linkages to new rad, and the boundary conditions and the symmetry stuff. But again, we build on examples mostly when we're writing codes, even Einstein Toolkit, even in the case of Einstein Toolkit. And again, your schedule.ccl file right here based on other codes. And this is actually kind of nice. It looks like we've modernized this a little bit, but by hand. This should be doable automatically with NRPy because it does have enough information to know that U right-hand side and VV right-hand side are being updated in the interior in this function. It does know that. It's just a matter of telling it to set up the reads and writes appropriately. And finally, the C driver function, we output the NRPy logo at the when you start up the code and register symmetries. Basically, these are all the core driver functions that you need to do an evolution, whether it be the scalar wave equation or be a system of equations. We did a number, Terrence did a number of convergence tests on this latest code, demonstrating beautiful fourth order convergence with RK4 and fourth order finite differencing, eighth order convergence with eighth order finite differencing, and RK8 that's built into the Einstein Toolkit's method of lines Thorn, which you can read more about. Here is a monochromatic plane wave shown over the entire grid domain. Notice that it's moving, I believe it's moving, yes, it's moving from the left to the right. The new rad boundary condition assumes an outgoing wave. So naturally, with the ingoing part, it's going to look pretty wonky at the outer boundary because we're violating that assumption. There's an ingoing wave at the boundary here. It's kind of neat to see this. I really like that. And here's a spherical Gaussian output, fourth order convergence with RK4 and fourth order finite differencing, eighth order with RK8 and eighth order finite differencing. And whew, that's all we have. I hope that you found this at least somewhat instructive. I think there's still, as indicated, work to do in terms of getting NRPy, making NRPy friendlier even still to the Einstein Toolkit. But for now, it certainly does the job. There is a bi-call, there are multiple Einstein Toolkit thorns now that are written using NRPy Plus. They're the bi-call thorns, which solve Einstein's equations, the right-hand side, divides right-hand sides of Einstein's equations, and also, of course, Fishbone Moncrief. Terrence will soon be telling us a little bit about his Maxwell equation solver in the toolkit. And Patrick will be telling us about his clone of Vial-Scale 4, which was originally written with Crank and using Mathematica, but here we made a clone of that using NRPy. So I think I'm out of time. Sorry if I ran a little bit over. And that's all I have. Thanks.
Virtual clapping.
Thank you.
So we're going to take about a 5-minute break, and then we're going to hear more about research at West Virginia University. Two of Zach's students will come and give us 15 minutes. Hello, and welcome back. Zach, are you there?
Yeah, I'm here. Sorry, I just had to unmute myself.
That's fine. So the next thing we would like to have is 2 short talks by your students. Oh, you know what? We never did questions for your talk. Does anybody have questions for Zach? If you do, please raise your hand or say something in the chat, please. We flew through at light speed there.
Yeah. Sorry, there's a lot of material.
Yeah, it's possibly people are just a little overwhelmed.
Yep, it's fine. I mean, it's designed to be somewhat standalone, so I just wanted to sort of show off what is there, and if anyone would like to take a closer look, yeah, you know where to find it.
All right, I'm not seeing any questions right now, so would you like to go ahead and introduce your, oh, here's a question. Why is NumPy still many times slower than NRPy Plus?
Okay, so NumPy is using Python to evaluate the floating point arithmetic, which in turn is an interpreted language. One very nice thing about NumPy and Python is anytime you access an array element, right? Remember I talked about these grid functions? It actually tells you if you go out of bounds. That's not true when you're writing in C, unless you add extra checks in your C code. So basically, by running through an interpreter, it is far, far, far slower. NRPy, on the other hand, outputs highly optimized C codes. So it is the code that NRPy generates is being evaluated at the CPU level about as optimally as you should ever dare to implement it. And so it's running C code direct, it's generating C code. And in those notebooks, it was actually generating and then compiling and running the C codes in the case of the scalar wave equation solver, where I did it 96 cubed resolution in only a few seconds, which, I recalculated, it's like 1,500 times faster than if you had run it completely in NumPy. But there is an exercise to the student at the bottom, by the way, of that, the first notebook I went over, to speed up that NumPy solver. I know it's possible to speed it up, probably by an order of magnitude if you work hard at it. But I think the stuff that you'll learn when optimizing that code you'll find generically useful when programming, when doing scientific computing. So Mario asked, can I use another Python-based CAS such as SageMath instead of SciPy? So SageMath, I believe, SageMath is sort of a conglomeration of multiple computer algebra systems, as I recall. And I think SciPy is one of those. I think if you wanted to use something else other than SciPy, it would require a little bit of work because NRPy really is at its low level based in SciPy. It would require a bit of a rewrite of some of NRPy's core infrastructure. That doesn't mean that you can't derive expressions that you might use ultimately with SageMath and then convert them to something that NRPy can understand. And let me just say one last thing about a feature of NRPy. We have recently embarked on work, and the student who worked on this made an enormous amount of progress in a LaTeX interpreter for NRPy. Basically, you code up a set of tensorial expressions exactly as you would in a paper, and it will convert that into NRPy, basically, or SciPy code, which NRPy can then interpret. It takes care of implied sums, partial differentiation, and even started work on covariant derivatives, which is not really a necessity, but it's very, very nice. It's possible to create a finite volume scheme using NRPy in its current form. Yes, in fact, there are two examples of using NRPy. There is a NRPy IGM code written by my incoming postdoc, Leo, that uses NRPy to generate Illinois GRMHD. That was very much in progress work. There is a NRPy giraffe that Patrick is actively working on right now. That's in the NRPy tutorial. And it uses NRPy to generate certain expressions that are otherwise painstaking to write by hand and in direct C code. So yes, and we're going to be improving upon that in the near future too.
Okay, there's another question in chat, but I'm going to encourage you, Zach, to answer that one offline so that we can move on to the student talks. Would you like to introduce your students?
Sure. I forget, who did you have listed first in the schedule?
It doesn't matter. Neither. I just said student talks. I didn't list anyone first.
Fair enough. Okay. So I guess let's start with Terrence. Since he's going to be, I just talked about an evolution code, a code to solve an initial value problem. And Terrence has been working very hard on creating a code that solves Maxwell's equations using two different formulations in the electrovacuum in the Einstein toolkit using NRPy to generate essential pieces of that code. So without further ado, I introduce Terrence.
Thanks. Can everyone hear me okay?
I can hear you great. Would you mind sharing your screen? Oh, great, thank you.
Yep. One second. Okay. Yeah, so we just heard Zach talk about solving like the scale wave equation, like generating ETK thorns. So here I'll just give a quick demonstration of solving Maxwell's equations in vacuum with ETK thorns generated by NRPy. And just a quick mention, Patrick Nelson wrote a lot of the base Jupyter notebooks, and I've just been working on those since then. Okay, so to motivate our discussion about Maxwell's equations, I'd first like to talk about like hyperbolicity of PDEs. So the basic idea of hyperbolicity is just like the notion of wave-like behavior for numerical solutions. And the idea is that if you have a weakly hyperbolic system of PDEs, then you might have error modes, which will kind of like sit in your numerical domain and just add error to your results. And they just sit there because they're zero speed, so they're not propagating away. And a really nice example of this was in the 3+1 decomposition of Einstein's equations. For like when that first happened, like using the ADM formalism, and it turned out that formalism was weakly hyperbolic, and it led to a lot of instabilities to the point where you couldn't really evolve those equations for a long time. So it turns out that system of equations was weakly hyperbolic, but then later on we had the BSSM formalism, which turned out to be strongly hyperbolic. So in analogy, here we'll just be talking about two different formalisms of Maxwell's equations, where system 1 is going to be weakly hyperbolic or ADM-like, and system 2 will be strongly hyperbolic or BSSM-like. So we start off with the evolution equations, and we're solving Maxwell's equations in vacuum and in flat space and Cartesian coordinates. Again, this is just a demonstration, so just keeping everything simple. So on the left-hand side, we have the evolution equations of the fields, and you'll notice that we're evolving the vector potential instead of the magnetic field, and that's just to guarantee that the divergence of the magnetic fields always stays down to round-off error. We're also working in Lorentz gauge, and so we have this gauge evolution equation for the scalar potential, and on the right-hand side, we have the constraint equation, and this comes from Gauss's law. That since we're working in vacuum, there are no sources, and so the divergence of the electric field should be 0. But again, this system of equations is weakly hyperbolic because if you look at this term and you compare like this second derivative to the derivatives that you see in the wave equation, it's a mixed second derivative, so it's not wave-like at all. And we'll see that does lead to like worse behavior of the errors. So to deal with this kind of error, or to deal with that kind of error, we'd like to introduce a new evolution variable that can make the equations more wave-like. So we call this variable gamma, and we define gamma as the divergence of the vector potential, and that leads us to system 2, which turns out to be strongly hyperbolic or BSSM-like. So on the left-hand side, again, we have the evolution equations, where blocks we have these modified equations. And on the right-hand side, we have another constraint equation where we can monitor how well our errors adhere to the definition of gamma. Okay, so we have our evolution equations. Now we need initial data. So here we just define a toroidal dipole field solution. It's pretty simple. So what we'll do is that we'll just define the initial data at t equals 0, and then we'll just march the solution forward in time with finite difference, like with the evolution equations and so on. So now that we have our evolution equations and our initial data, we need boundary conditions. So to really see whether or not these error modes propagate, we'll use a radiative boundary condition, or the Sommerfeld boundary condition. And the basic idea is that it just assumes a spherically symmetric wave with some radial fall off. And again, we want to see those waves just propagate through that transparent boundary. And this leads to minimal reflections. And if you'd like a more detailed derivation, please see NRPy's Summerfield tutorial, which Zach and I wrote. Okay. So now we'll generate, so now I'll just talk about like how we generate the E2K thorns. So as Zach mentioned before, NRPy just generates highly optimized C code from really readable tensorial expressions, which allows us to minimize human error, so like bugs and so on. And we use the freely available SymPy package in Python. And again, all the thorns are fully documented. And these 2 thorns will be updated soon on the NRPy page. Yep. Some more details on the thorns. Again, they're heavily documented. And as Zach mentioned before, the CCL files are either like totally automatically generated, like the param.ccl file, or they're easily built from templates. I've been using the Bical template, which I think itself uses Maclaren or Lean, one of those. And they're both the thorns, the initial data thorn and the evolution thorn, they're written such that at runtime you can choose different options for initial data. Right now we only have the toroidal dipole fields initial data, but maybe we might add others. We're still thinking about it. And then for the evolution equations, it also outputs 2nd, 4th, 6th, and 8th order fine differences. So in the param file, in the par files, you can just choose whatever fine differencing you want, and you should be good to go. Okay, and this is show everyone like how easy it is to do this. On the left hand side, and on top we have like system 1, where you can see that like you can match the indices and the equations like pretty easily to each other. So whether you're working with like vectors or tensors, and you'll notice this kind of like subscript D, capital D down, and it just corresponds to like derivatives.
Just a second, Terrence. We have a question for you from a mad scientist.
Oh, okay. Can you read it or?
No, it's they raised their hand. The mad scientist, your question?
Hey, I'm sorry, I raised my hand when Zach was giving his talk, and
I'm sorry, I didn't see it.
yeah, no problem.
I just saw it now. Okay.
Okay, yeah. Yeah, so again, you'll see this underscore, this got underscore DD, and that just corresponds to these derivatives. Ideally, if you're working in curved space-time, then we would introduce the metric tensor to like make things a little bit more formal. But here we're just in Cartesian coordinates and flat space, so we can get away with like these kind of notation. So you can imagine that like if you're coding these up, then you'd like to have a LaTeX. You have a LaTeX block, and then you'd have the equations. And in fact, this is what it would look like. So up here, you have these equations, and then right below, you can just start coding in these equations. And you could imagine a scenario where you're coding up like a really huge equation, and you could just like code it up in blocks. So you have like block 1, you code that up, block 2, etc. And it makes it really nice and really easy to follow. So once I did all that, then we can just run everything within the Einstein toolkit, where we monitor the L2 norm of the constraint violation. And I was really pleased to know that the Einstein toolkit does have like reductions. So here we just use the norm 2 reduction, which makes things really easy, I think. And so we monitor this constraint. And so on the left-hand side, you have a plot from Knapp, Walker, and Baumgart from 2002 for system 1. And here we use iterative Crank-Nicholson time stepping plus 4th order fine differencing. We don't get exact numerical agreement, but we do see the qualitative agreement. Whereas system 1, which is weakly hyperbolic, you see these non-propagating or zero mode error modes, zero speed error modes, and they're just staying there. Like, yeah, they're staying there, adding error to your simulation. And zooming in, you see that there is initial behavior, but it just settles down to some constant value. Now compare this to system 2, where we do see we do see these error modes propagate away at the speed of light, and you do see the L2 norm of the constraint violation decrease exponentially. And if we zoom in a little bit, you'll see that it does increase a little bit more than what you see in system 1, but again, it decreases exponentially, so no worries there. So in summary, we've just written and documented all these ETK thorns that provide like a really nice demonstration of probability of Maxwell's equations. And more importantly, we've confirmed similar qualitative behavior to Knapp, Walker, and Baumgart, specifically the propagation of error modes. In the future, we'd like to add functionality for spherical coordinates, and we'd also like to generalize to curved spacetime to like do some interesting projects with this, like for example, like super radiance with black holes. And we're considering maybe adding other initial data options. And that's my talk. Thank you.
Virtual applause. Thank you, Terrence. Are there any questions for Terrence? Okay, I don't see any questions. Oh, go ahead.
Sorry, I didn't raise my hand. So a question for you. For this thorn, do you see it being coupled to some type of ideal MHD code as well to use as a way to model, say, the Maxwell field outside of a neutron star or things like that?
I'm not really sure. I think Zach and I are still deciding on different projects to work on. Does that answer your question? Sorry, again, this was just a demonstration to like just show how NRPy can be used to generate these ETK thorns. In terms of actual science, I don't really know.
No, the answer is fine. The answer we are still deliberating is fine. Thanks.
Yep. Next question, Eric Schnutter.
Hi, Terrence. Can you point again to the URL to the Python notebook?
Yeah. So there. Oh,
You could just paste it in the chat. That would be ideal.
Oh yeah, I can do that.
That would work. Thank you. Yes.
Yeah. They're not updated to what I'm using now, but they will be soon.
Okay. Thank you.
All right. Thank you, Terrence. Zach, would you like to introduce Patrick?
Great. Great work, Terrence. Patrick has been, Patrick was sort of the first person to, one of the first people to learn how to use NRPy. And as a result of his feedback, NRPy has been improved enormously. One of his first projects was to make a clone of the Weil scale 4 Einstein toolkit thorn, which he'll tell you a little bit more about, but using NRPy Plus instead of Crank. So go ahead when you're ready, Patrick.
Thank you. You guys see my screen and hear me okay?
Looks good.
Yes. Yes.
Okay, thank you. Okay, so yeah, as Zach said, today I'm going to be talking about a NRPy Plus clone of Weil scale 4, which we have named creatively Weil scale 4 NRPy. So the Weil scalars are a set of 5 complex scalars that encode information about space-time. They are contractions of the Weil tensor, usually written as C, with some null tetrad. The Weil tensor itself is a rank 4 tensor that's related to the Riemann curvature tensor.
Patrick, we're losing your audio.
Riemann curvature tensor encodes information. Sorry, that's okay. Can you hear me now?
Yes.
Okay. So yeah, well, it's related to the Riemann curvature tensor. While the Riemann curvature tensor encodes information about the volume and shape of a body, the Weil tensor really only encodes information about the shape of a body. and it has the same symmetries as the Riemann curvature tensor, which gives it 20 independent components that will need to be coded. This makes it possibly one of the most complex expressions computed in the toolkit, scalar psi4, because it is used for gravitational wave extraction. Its real and complex components correspond to the two different polarizations of gravitational radiation. So Weyl scale 4 computes all 5 Weyl scalars as well as some invariants that are computed from those scalars. And it does this by computing using the Frank code, which is a Mathematica-based code that takes as inputs the tensorial equations in an Einstein-like notation, which is, of course, similar to what how we actually write those expressions, as I had a little equation on the last slide. So why would we want to use automatic code generation? Why not just go writing the codes ourselves? Well, as I mentioned before, the expressions are very complicated, and doing this by hand would be impractically complicated. So we automate as much as we can in order to reduce the human error in transcribing these. And the tools like crank code and NRPy allow us to write these expressions using a syntax that's much more familiar to how we actually write these equations out in papers. So why then, when we have a completely operational Weyl scale 4, would we want to write a clone of that in NRPy? The biggest issue comes down to expense. So while Crank itself is open source and free, very expensive license. On the other hand, NRPy uses Python, which is itself free, as well as the open source NumPy package. So that right there is already a lot less money to spend to get started. Everything else in the infrastructure is free and open source. Like crank code, we have an Einstein-like notation as input, and the output is highly optimized C code kernels that make use of tools like single input multiple data, single instruction multiple data, SIMD, and common sub-expression elimination, or CSE, to optimize the codes. We also document everything in a lot of detail in user-friendly Jupyter notebooks that allow us to use LaTeX and HTML to make the documentation more readable and also intersperse it with our code, which allows us to reduce the human error in transcribing these equations quite a bit. So here's an example of that Jupyter notebook documentation. So up at the top, we have the full expression for the Riemann curvature tensor, which we need for the Weyl curvature tensor. And then down below, we have the code that we use to write that, to code that expression up. As you see, the two sets of nested for loops that loop over all the indices and add on the derivatives of the metric tensor and the Christoffel symbols and all the combinations thereof. And we can also see critically that on basically any screen, you'll be able to look at this teched up version of the expression for the Riemann curvature tensor and write the code at the same time without having to flip back and forth between different windows or scroll up and down, which makes coding up these expressions just a lot simpler. So then, once we've written up all of those expressions in a nice Python module, we can move on, and we'll do this in a separate notebook just to keep things organized, and write the ETK thorn. So the first step to do after we have those expressions is going to be to import them into our new notebook and use the built-in utilities to generate the basic C code kernel, and then we can use the NRPy function outC function to create a C function. So all we have to do is specify the inputs and the outputs, give it a name, tell it where to put the file, and then a few other parameters for like the loop over the portion of the grid we care about, and it creates that function for us. And of course, we will need to write the CCL files for the thorn. So this one is param.ccl, which, as Terrence mentioned before, we now have a tool to do automatically. But this was my first project on the toolkit. So way back then, we didn't actually have that, which is why this one is written out manually. But it does also give me a chance to show off the write file. It's called the cell magic in Jupyter. If you note at the top, you have the 2% signs and write file. So that allows us to store raw text in the notebook and then automatically output that to a file whenever somebody runs the notebook to generate the full thorn. So once we have output our thorn, we of course need to validate the expressions and test it, make sure everything works right. So we did 2 tests with this to make sure everything was running as we wanted. So the first we did was an analytic comparison of the 2 expressions. We did this using Mathematica because SymPy has built-in utilities to output the expressions in a Mathematica format, while the reverse isn't really true. So we put both sets of expressions into the same Mathematica notebook, obviously changing names so that there wasn't an unfortunate collision. And we subtracted the 2, simplified the result, and found that we had perfect agreement with a nice output of 0 in the difference in the symbolic expressions. Then we also did a numerical test where we set up a simple head-on collision using Brill-Lindquist initial data for 2 black holes, and we let that run for a while and output the really all the Weyl scalars and invariants after the merger, and validated that we got basically the same thing out of both. So here we have a plot demonstrating that. So this uses the real part of the psi4 scalar. And on the y-axis, we have the significant digits of agreement between the original Weyl scale 4 and our new Weyl scale 4 NRPy's output of the real part of psi4. And this is just along the x-axis as output by the toolkit. And we see that we have good agreement between the 2, hovering around 8 digits of agreement between the 2 codes. And we see the same level of agreement throughout the rest of the grid, as well as in the other 4 Weyl scalars and all the invariants that we output. So the next steps that we would want to do are, is that the way we do this in NRPy, we are in a good position already to move this into arbitrary coordinates, simply by following the comma goes to semicolon rule and replacing derivatives with covariant derivatives, which will be quite useful as spherical coordinates are coming to the toolkit soon. And then on this slide, I also have some links to the 2 notebooks that I was talking about in this. If it would be useful, I can paste them into the chat. Okay, so that was all I had. Thank you for your attention. Does anybody have any questions?
Does anyone have any questions? So we have in the chat, we have, is there any performance difference between the crank version and the NRPy Plus version?
I didn't actually measure that, but I would imagine based on all the other steps we've taken to optimize things, it would be at least comparable to the crank version.
Okay. There's a request that you paste your links into the chat, the links to the notebooks.
Do that real quick.
Are there any other questions? All right, thank you, Terrence and Pat, for your talks. Our next, oh, we have another question. Can it be adapted to Newman-Penrose formalism? Is there any difference? Oh, well, can it be adapted to Newman-Penrose formalism?
I'm not entirely sure what that would entail, but I can't imagine it would be too much of a difference for the Newman-Penrose formalism. And I use the same null tetrad, the other question, as in the crank version.
Okay, thank you. All right, so our next and final item is the panel discussion with the Hello, everyone. It is now 11 minutes after, and we plan at this point to have a panel discussion with the maintainers of the Einstein Toolkit workshop. So this is going to be a somewhat free-form discussion. It can consist of questions from you all, or if you don't have an immediate question in your mind, we have a couple of them prepared. So just for the record, our maintainers are Roland Haas, Eric Schneider, Zach Etienne, Bruno Giacomazzo, sorry if I mispronounced your name, Peter Diener, and Ian Hinder, and myself. So, oh, and Helvey, I'm sorry, Helvey. I was reading off the email list from your mail, and your name was at the top instead of it being in the list.
It's okay.
Okay. So anyway, I'm glad to have all of you here. To start off with, is there anybody who has a question? I see no raised hands. So I guess the question I would put to the panel, and I would like us to consider is, what as you develop as maintainers, what are the things that you are looking forward to implementing, to adding to the toolkit in the near future? So you can raise your hands, I guess, and we'll just go in any order. Or I can pick people. Bruno.
Yes, so as I said, we're working on these new code spreads, and we would like to add this to the toolkit once it's let's say, ready for binary neutron star simulation. But something that is very important for us is a more accurate, let's say, evolution of neutrino emission, in particular using some, because at the moment we are using the Zelmani leakage scheme, which is open source, but it's only a very simple leakage scheme, while there are more advanced methods like moment schemes and so on. And I think there are many people that are interested in those. So I wonder if maybe we can try to work together on a sort of neutrino code for the Einstein toolkit that can be used by any other evolution code like Illinois or Spritz or Gerhydro or whatever. I don't know what other people think about that.
Do you have a particular scheme or algorithm in mind? Better than leakage? A particular moment scheme, a paper or something?
So I was thinking, so I'm not an expert on this, but from what I read from the paper by Francois Foucault, it seems like the M1 scheme is probably one of the best at the moment, used in binary neutron star simulations. And for sure, there could be something better than that. So.
Okay. And do you think you know when your code might be included in the Einstein toolkit? Do you have like a planned date or year?
For Spritz, don't know, because as I said, we are finishing testing the neutrino, and once the paper is published, we will update the version Zenodo. And then after that, we will start working on binary neutron star. And if everything works as planned, then I think at that point we will work on the inclusion of the Einstein toolkit. Because I think
Okay.
that in order to include that in the Einstein toolkit, for sure, we will have some work to do. I think a documentation or maybe some, I don't know, how the schedule or other things are written. I don't remember what are the requirements actually for the inclusion of a code in the Einstein toolkit. But I'm pretty sure there will be some work needed. And so I want to be sure that the rest of the code is essentially fine. And so we just have to do some minor modification, maybe for inclusion in the Einstein toolkit, and that's it. So I hope next year, but I don't know.
Okay. That's all I was looking for as a guesstimate. Who would like to go next? Helvi.
Yeah, so I can also add a few things. So as some of you may know, I've been working on a library for gravity beyond general relativity and using GR to test for light fields, for scalar fields, and for vector fields. That code is called Canuda and has been developed together with Miguel Ziliao and my PhD students, Matt Alley and Giuseppe Ficara. Part of that code is already in the toolkit. So if you see Procathorn or Lean, that's already there. But we also have additional arrangements for adding scalar fields, which is well tested and available publicly via our Git repository and on Zenodo. And we also have a arrangement for modified gravity, quadratic gravity. So if there's any interest to go beyond GR to do a strong field test of GR, these could be included. So the scalar field is Thorn is very well tested, and we are updating the modified gravity part.
Okay. Who would like to go next? Roland, could I volunteer you?
Yeah, Zach had a hand up that he put it down.
I saw it just as I said your name. I saw it just as.
Okay, he's hiding now. So there is, I think there's two things to consider, right? So one of them is the point of view of being a maintainer of the toolkit, which at least when we initially came up with this really means you're looking at the toolkit as a whole and you're maintaining the toolkit. You're not, say, talking in, at least from, it's not the percentage who develops the new codes, in the sense that the toolkit would take codes that are already used by groups involved in doing research, and then either approach those groups for codes that seem useful or help groups make their existing codes available. So in that sense, now I'm talking as, say, a maintainer, and not so much as somebody who might be involved in research with various people here. So in that sense, for me, the interesting thing, of course, is going to be the Carpet X driver code that Eric in particular is developing. Yes, yes. And related to that, having a chance of finally getting some working and hopefully straightforward to use GPU support into the Einstein toolkit. The later one in particular is something where there is still, well, there's not much done yet. AMRX supports it, but there hasn't been anybody really who has made much progress adding it up. I know from some people that they're interested in doing so, but that's definitely something where we are not at the stage yet where we can say we have anything that's yet working where the toolkit as a toolkit could actually do something. And I think that would be of interest for lots of people to have GPU support in the toolkit. So that in some sense, I would like to get things into the toolkit that are of interest for people that want to do research, to make sure that it's available for them when they want to get started with things.
So Zach, do you wanna, since I missed your hand earlier?
It's all right. Yeah, so a couple of things. I've proposed inclusion of NRPy in the next version of the toolkit. So it's within NRPy. Basically, it's exactly as it's described here, validated post-Newtonian expressions for input into other things if you want to use them. So for example, on the main page of NRPy, which is linked to from the main NRPy, the main menu of NRPy. This is something that's very useful, I think, for those of us who do binary black hole calculations. The big question is, what are the momentum parameters that you need for your initial data when you evolve a black hole binary, such that it minimizes the eccentricity. And what I've coded up in NRPy, the main reason I coded up NRPy in the first place was so that I can get these parameters out very quickly at the highest post-Newtonian order that's available. And this builds upon work done by a number of folks. And I cite all their papers here, and you can click on them and you'll see it's all nicely linked. But primarily Ramos, Boades, Hussein, Pratton, theirs I think is the state of the art. It goes up to 3.5 PN order. So you give it the binary parameters as input, and it will output for you using NRPy the quantities that you need to inject, right? So a black hole binary is not going to have zero radial momentum because it's radiating gravitational waves. So you have to include that physics in your initial data consideration. So that's one thing I've proposed for inclusion, and that's going to be merged with a parallel effort in collaboration with Eli Huerta, Roland Haas, and Sarah Habib in Illinois, who are working on, so this is like a zeroth iteration for a eccentricity reduction code as described by Ramos, Boades et al. But this already gets you to pretty low eccentricities. So I think it may be good enough as a start if you want to do a black hole binary calculation with, and you're willing to accept 10⁻³ eccentricities. The other thing, Illinois GMHD has recently been documented by Leo Vernick in pedagogical Jupyter notebooks alongside NRPy. Now, this is not a version that uses NRPy in particular, but it does use the NRPy style of splitting things up and providing links to all the various notebooks. So basically, if you go back to the main directory here, you'll see that every algorithm in Illinois GMHD is now documented properly. So I propose this for inclusion, but unfortunately this version of Illinois GMHD, which supports hybrid piecewise polytrope-based equations of state, is not fully backward compatible with the old version. And we've moved on now to adding tabulated equation of state support and neutrino leakage along the lines of Spritz. And Leo's in charge of that effort. And we hope to have that in the toolkit, you know, in the year time frame as opposed to the month time frame. So certainly not the next release, but stay tuned in the near future. And that's not to mention, you know, all the fun things we have planned for NRPy development, like GPU kernel support and just very basic improvements to make it more Einstein Toolkit friendly.
Okay, so the last two people who haven't commented yet are Eric and myself. So Eric, would you like to say anything about, I mean, you've already talked about Carpet X, and that's clearly been your focus and will likely be for quite some time, but any other thoughts you want to make on the future of the toolkit?
Well, regarding Carpet X, what I didn't mention is that I would be happy to invite collaborators, both on the infrastructure and on using an actual physics term to use it. Now, for the physics, that would at the moment be something like a guinea pig, because I mentioned checkpointing restart isn't working, so you can't use for productions. But I would be interested, for example, to have a hydrothorn in there, just to see that we have everything in place for hydro and that runs efficiently, etc. And I think everything else Roland already said about Carpet X. Now, the future of the Einstein toolkit, I think what is always important if there's a new grant coming up is a project that interests everybody, where everybody can go together and do something like a common thing. And it's very difficult to do cutting edge research because that requires a small number of people who focus on something and can work in secrecy to harvest the paper. But if there's a well-known algorithm, for example, M1, hi Bruno, And people could re-implement it and test it against something else. And then after a few months, we have a paper out where we compare to others, and it's something on which everybody can build. And where, I don't know, everybody, but say a large fraction of the community, plus people not here, would be interested. That is always a big community success. Now, it's always difficult to do that, because if everybody benefits, nobody thinks they want to chip in or something. But if there are a few people pushing that, then in the end, they are a lead author on a publication that is cited many, many times. That could be cool. So I think in terms of toolkit development, I mean, of course, I personally think it's carpet X, but also in terms of community, I think it's some physics thing, and definitely radiation transport is a very important goal there.
So as for myself, I've got a couple of things which I hope to see develop in the Einstein Toolkit. So one of which is, I mean, while our codes are well supported for 3D numerical relativity, I actually have a side project for evolving water waves, which is a 2D problem using the Einstein Toolkit. And currently, Carpet X, in its state of partial development, doesn't support that too well, because you can only specify number of ghost zones in all directions. You can't specify NX, NY, and Z.
Oh,
So
you can.
Okay, last I looked at the par file, that wasn't there.
Sorry, that can be. You can have different grid functions, can have different numbers of ghost zones. It's much more flexible. That was one of the lessons learned from Carpet. That is just
right,
but we can fix that.
I think the par file doesn't support that yet. But you know, it's one of these things. If you don't try to keep it working from early on, it's going to wind up developing its own little pathologies. But anyway, so that's one interest of mine. I'd like to see that really take off. And the GPU support is another thing I'd like to be involved in, because I had a project to work on that, and it never really got out of the academic stage for Cactus. Another thing, though, that we've promised in the recent proposal, and which I keep thinking about, we promised a portal or science gateway for the Einstein Toolkit, without really a particularly clear idea, I think, of what we plan to put in that. I've always had a vision that, well, not always, I had a vision. Paul Walker, one of the original creator of Cactus, had a vision when he created something called the G code, that he could just write down some partial differential equation and the computer would spit out the answer. And he realized that was a little too ambitious after working on it for a few years, and then he scaled it back and he came up with he came up with Cactus. And I think we're almost back to the point where we can think a little bit closer to his vision, right? So when we had Crank and we had Mathematica, that could create mathematical expressions, to convert mathematical expressions on the fly into code, but it had that license restriction. So if you wanted to put it in a portal or a web server, you would have legal problems. Now we have NRPy, which does something similar. I could envision that we have a web server somewhere where you type in some differential expressions in SymPy, and that NRPy cranks on it at several levels and then can produce a result. Granted, it's still a complex problem to make those pieces work, but I think we're kind of in the place where we could almost imagine it happening. So that's one of the things I'd like to see there. I think based on, and maybe people in the audience would like to chime in, I think another thing people would like to see is ways to get neutron star and black hole initial data that matches astrophysical events or particular systems that we know about. Make that whole process a little more streamlined and easier.
Yeah,
anyway,
I think it's certainly in NRPy's wheelhouse. As the years have progressed, more and more things within NRPy have become automated. I have my own private branch where I'm pushing on this black holes at home idea, where you can do black hole binary calculations on a desktop computer using special numerical grids, non-AMR, non-Cartesian AMR grids. But and with that, I'm developing sort of a next generation interface where it generates make files automatically for you, and full C files, not just C functions. And so with that, I think the capabilities are going to become more advanced. And I mean, the thing is, I'm worried that, you know, as I continue, you know, this process of, right, at some point, right, you can just abstractify everything, right? And, you know, you plug in your PDE and then something happens. There's a big black box. And then there's something that comes out the tail end of that. And it's important to know what's in that box, I think. That's a major consideration, I think, we always have to have. So that's the reason why I wrote the full NumPy based code, just to make everything as explicit as possible. Basically, you know, if you were a student and you were given an assignment in, you know, computational physics class to solve the wave equation in 3D using Python or what have you, you know, this is what you would see. This is what you would do. You wouldn't abstractify so much. But sort of, I think the key here is I'm going to improve NRPy documentation by moving the levels of abstraction, but have at the beginning, you know, it's not going to be abstracted at all. It's just everything is explicit right in front of you. And now we're going to abstractify this, until finally it's almost at the level of what you described, Steve, which is, you know, give it a PDE, it'll solve it. And, but the thing is, you'll understand what's in the black box, which I think is critically important. Otherwise, you know, all sorts of numerical errors might prevent us from interpreting the results correctly.
Bruno.
Yes, regarding the initial data, I think there was also a request, was yesterday or the day before, from someone in the audience asking for a tutorial for using Lorraine to generate initial data. So this is something that we could do. I can also do that. I mean, I can, for example, try to prepare a tutorial on generating initial data, for example, for a single neutron star, as well as a binary neutron star system. And as far as I know, Joshua Faber is also working on a different version, I think, of the code for neutron star black hole initial data for Lorraine, if I remember correctly. So that is also something that maybe we can try to contact him in order to get our hands on. But for sure, a tutorial on how to generate initial data with Lorraine and maybe possibly also collect initial data is for sure useful.
Yeah, I think from what we saw early on, there's interest in that.
Yeah, I want to mention that for some of my papers, actually, I publish in the supplementary material the initial data for Lorraine that we used for those papers. So this is for my latest paper. If you go there, the initial data are in the supplementary. But for sure, yes, a tutorial for Lorraine is something that I think I can quite easily produce, because it's not so complicated when you know what you have to do. At least for neutron star. For neutron star black hole, to be honest, it's a bit more complicated.
I noticed when stepping through the maintainers, I skipped someone because, yes, his hand is now raised because his picture was off, and so he didn't. I just didn't notice. So, Peter, would you like to comment?
Well, I've just I can update you on what is going on. I also already mentioned that in my talk yesterday, that there's, for the Cellforce code, there's certain things under development, so such as checkpoint restart capability. And when that is ready, it would be nice to have that included as well. Then there's my IU students, Joe Gibbs, who worked on the Tchaikovsky equation in Kerr. That, in principle, could be added as well. Of course, it would have to be added in stages, where first we just do the equation for the field, and then later on, with Barry's help, we will add an effective source for that, so we can do particles. But then there's also what Samuel Kopp has been working on, the Lorentz gauge metric perturbations, once we get that sorted out, and also the Vigevilla-Cervilli formulation of the perturbation equations. So there's a bunch of stuff on the way, in progress, but it's not yet clear exactly when these things will be ready.
Also, in terms of a science gateway / portal, Peter, I think your code would be nice because it's designed to run on a single node. And one could imagine, that we just have some machine that's dedicated to that, sitting somewhere that people could just go to and say, run with these parameters and show me waveforms and so on. I'm not sure if
that's certainly something we can think about.
Yeah. I'm not sure who exactly the users of that would be, but it struck me that having having a code that does real science on a single node makes that easier.
Yeah, we can talk about that.
Okay. So here's another question. Is anybody aware of any, so Peter's code is a non-cactus code in the Einstein toolkit, and it was always conceived when the Einstein toolkit was created that it would be a collection of codes. Although until this last year, it's only been cactus, and now it's cactus plus the self-force code. Is anyone aware of another candidate code that could become part of the ETK?
There's a code, I believe, called GR1D. Even O'Connor was working on it. It might have been 5 years ago, something. But the beauty of that is it's a 1D code, easy to understand, and it does stellar collapse. It has Einstein equations and matter in there. And in particular, there's a student who wants to modify the Einstein equations. Hi, Helby. Then this is always a good starting point. And I've pointed people to that code, and Evan is a cool guy. So we could approach him and ask him whether that should be put in there. I don't know what that means. I mean, the code is, maybe it gives the code additional exposure, but I think that would be a good candidate.
Okay, thank you. Other thoughts?
May I just respond directly? So I think this is a great idea, Eric. And in fact, Roxana Roscamet, who was a PhD student in Cambridge, did include equations for scalar tensor theory. So she already had extended that code, as far as I know. But I don't think that that extended version is public. But overall, I think this is a great idea to have that addition for a 1D stellar collapse in there publicly.
Roland?
Maybe just to chime in, I think Eric probably already said it, but the GR1D code that was mentioned is not the extended version, but the plain version is already available publicly on Stellar Collapse with the other codes that are basically up there. But that's probably an older version, and as Eric said, one would have to contact Evan, I guess, for the newest version and to properly include it if he wanted to do that.
And translate it into Julia.
Most definitely.
So GPU coding, GPU code is obviously something that we've wanted in the toolkit for a long time, simply because there are so many top 500 machines that rely on that type of code. As I said, I was part of a project that was working on that. And while we did have something, it was enormously complex, and it never really made it out of the researchy stage. So we got a couple of different papers on how to do things, but it didn't really turn into something that we could just generally use. In particular, it never really worked with AMR or anything like that. And there's a number of different reasons for that. But so in AMREX, there is built-in support for GPUs. And this seems likely the way to go, although I think there's still going to be a lot of complexity there. We were talking with the developers there, and they say that in addition to CUDA support, they do plan to support the GPUs produced by AMD. So there is an effort there to support diverse hardware and make it available. It looks like, from what I can see, it looks like the coding mechanism is similar to what's done in Cocos. You provide a lambda to do a calculation on a point, and that gets translated into something that runs on the device. Does anybody have any thoughts about GPUs for the Einstein Toolkit?
So I've looked a little bit into, so NVIDIA has a really nice set of tutorials on, for example, solving the scalar wave equation on a GPU at high finite differencing order. And I think that's one of the main complications that you're going to run into when solving Einstein's equations is breaking up the grids, slicing and dicing up the three-dimensional domain in such a way that you can efficiently access the memory as you need to, and then perform the calculation on the many CUDA cores or GPU cores. So that's something I've just started looking into, but the more I learn, the more I realize I don't see as a point of principle why this couldn't be done in some automated way with NRPy. So I will continue working on this. I'll reach out at some point in the near future to anyone who's interested on the Einstein Toolkit mailing list. And maybe we should have some sort of regular discussion on this, something like a telecon, not every week, I hope, but on a regular basis, just to share what we've learned about generating code for GPUs, because there's a lot of good documentation out there, and it sounds like you've made some great strides in the right direction as well, Steve. So I'd like to learn from those of you who looked into this far more in far more depth than I have, because if I can learn it, I think NRPy can learn it, and then we can have an automated code generation infrastructure for doing it.
Bruno.
Yes, a question. Does Exceed provide any support for groups that would like to port their code to GPU? I'm asking because in Europe, I know that there is some funding available, and I know that the Supercomputing Center in Bologna in Italy tried to apply for that, for some astrophysics code. But unfortunately, the Einstein Toolkit was not included in the, well, anyway, that grant was not approved anyway, but the Einstein Toolkit was not included in the code they wanted to port to GPU, because they told me they see the Einstein Toolkit as a code developed and mainly maintained in the United States, since it's supported by the National Science Foundation. And so they were concerned that the European Union was not going to fund support for a code that is developed in the US. Anyway, that grant was rejected anyway, so but I wonder if there is something similar for Exceed, like that maybe you can try and convince some Exceed people to help importing the code to GPUs.
Well, the Einstein Toolkit is one thing, but if you think of Carpet X, which is based on AMREX, then AMREX might be supported. And instead of trying to add GPU support into the Einstein Toolkit as it is, we might try to leverage AMREX. And AMREX is much larger. It's used by many more people. That is, it might already be part of the grant, even if the Einstein Toolkit is not. And then we just say, yeah, we use AMREX. Please help us use AMREX as part of the Einstein Toolkit. And AMREX also has tutorials how to define a difference in code and so on there. So the hope that I have is kind of that, since with the new parallelization mechanisms, you write routines that are much smaller, much simpler than what you did with Carpet, it would work with GPUs out of the box, because all the ways in which you need to do things different are handled by AMREX. And then in your user code, you essentially just say what you do for the individual breakpoints. There's no multi-threading, no scheduling, no nothing. And kind of the loop kernel, that would be unchanged. It can be CUDA or C++, it's basically the same language.
Okay, so there's two hands raised. Roland was raised first, so I'm gonna call on him.
Okay, so I'm going to respond to Bruno's question about whether Exceed has any support for porting codes to GPUs, and the answer is basically yes. There is something like extended user support. I think ECTS is the abbreviation that they use. That in principle gives you a software analyst that works with you porting your code to new machines. And we've tried to do that once, not for GPUs, but for the Intel mix, what were the PHYs when they first came out, so not the night sliding, but the generation before, with Lars Köstecker from TAC. And the problem is usually that our code is too complicated. Most codes apparently are still assumed to be a single loop with a kernel that you iterate over, and that's where you spend 99% of your time, which we don't. So it's reasonably straightforward to port the science parts of our codes. That's why it worked well with McLachlan. And you could also port GeoHydra if you wanted to. The trouble is usually porting the infrastructure, meaning the adaptive mesh refinement code. And Carpet is one of the more complicated ones because it actually does the subcycling in time, which a lot of the simpler codes do not. And that seems to be where the problem is. So I think that's where we are actually gaining something from AMRX, because there we are gaining the GPU support in the infrastructure.
Helvi?
Yeah, I also wanted to respond to Bruno in terms of funding in Europe. You know that PRAISE also has these shortest timescale grants for code development and testing. Have you tried any of those?
No, I didn't try those, but those are just to access some resources for a limited amount of time. I don't know how much support they provide in rewriting the code. Do you know?
So I believe there's 4 different types, and I think there's at least one that also provides support. So you would have to check the PRAISE website, and I don't know how that changed since last year, but I would recommend to look into that on the European side.
Okay, I will check. Thanks.
Yeah. Okay. Great.
So we have a question on the chat, which was relayed to me by Roland, because I can't watch the chat and the hand raise and everything else. Bill asks whether there's a part of the core of the toolkit that we should think about replacing or changing to make going forward and maintaining and adding new research easier or quicker. Well, we're replacing Carpet with Carpet X. I guess that's one answer. And in the process of that, we can overhaul a few things. Anyone else like to say anything?
Yeah, Presync, right? That's a major update that I think we're going to need anyway in the transition, right, to Carpet X.
Yeah, so Presync is now available in the current version, and it's being baked into Carpet X. It is not without its many complications. It's surprising to me how many different ways old thorns can fail to interact with that. But we've been discovering, Roland and I and Sam Cupp have been discovering the joy of those things. Roland, would you like to comment?
Wasn't commenting on Presync, but I think, yeah, so one of the things that we learned with Presync is that we probably have to make a cut at one point and limit what will be backwards compatible. Usually we try to be very backwards compatible, but we'll have to make a cut, and we will probably have to say at one point, okay, these features will no longer be supported. There's in principle a facility in place to do so, but it takes a while usually to change things. The other thing that you might see is that I guess we may slowly transition away from what we consider the default thorns for certain things. So right now, if you look at the toolkit and kind of the default stuff that we have would be you use McLachlan for evolution. If you have a vacuum code, you have GeoHydro if you're using a fluid, and you're using multiple, say, and Wildscaler for gravitational waves. And I can see this changing, that if these codes in particular do not see much development and they're overtaken by other codes that are in the toolkit, that the default would switch, and that there would be a slow change there over time. There is proposals to remove code. We carry around some garbage. So we want to, for example, get rid of a lot of the Fortran code in GeoHydro, which is now being duplicated basically in C++ code, which runs more quickly. We also have some old facilities in the toolkit that have been deprecated for years and that we want to remove. For example, some point-based, include-based mechanism to provide a stress energy tensor, which you should never, ever possibly use, given that you might spend up 40% of your time in a string compare. So there is things that we would like to do, but to some extent are lacking person power to clean up the code and patch all the fires that you're creating by taking out things and then suddenly changing a thorn that's not officially deprecated yet, but hasn't been used really by anyone for a long time.
So I guess I'd like to point out in this context that the Einstein Toolkit is head and shoulders above a number of other scientific coding projects I'm aware of because of its standards of testing and reviewing and ensuring that things run on multiple platforms. Many other codes just don't do that. I mean, there's another code I know of, which I won't name, that I work with. They don't have a test suite, and whenever a release comes out, the compile breaks on several platforms, and the old tests produce different results, and so on. It's hard to get enough people together with enough discipline to achieve what the Einstein Toolkit has achieved in terms of this level of rigor. So I think that's one of the good things about this project within the scientific community. So that's maybe another thing that we can talk about is is encouraging contribution to the Einstein Toolkit. So these people up here that you see that we've identified are people who are maintainers of the Einstein Toolkit. We don't all work in any one location. In fact, I think that at most two of us work in any given location. And we're always looking for new people to become bigger contributors to the toolkit. If you do, there is a path for you to get credit through our DOI. There are multiple opportunities for you to advance your careers and contribute. Yeah, so we've had turnover of a number of different people over the years since this project began, essentially in 1997. So I'd like to, I encourage you out there who are listening to think about how you can contribute, or if you'd like to, or whatever. We would love to hear from you. We would love to have you on our regular weekly calls. Would anyone else like to say anything about contributing to the Einstein Toolkit? Maybe say something about how you got involved and what it's done for you. Come on, raise your hands. People are being shy. All right. Well, hopefully, you users out there, or your attendees, will not be shy about this project. You'll think about ways that maybe you can become more connected to it. While this particular workshop has been online, a number of them are normally they're physically located either in the US or in Europe. We've generally had one in each location per year. And these have been nice trips that afford us a bit ability to see other cultures and other ways of looking at science, and to gain a lot of social interaction and experience that way. So there are a lot of things to benefit from working more closely with this community and becoming involved in the groundbreaking science that's currently happening in general relativity. All right. We are coming up to the end of...
Steve?
Yes.
I would like to make one comment about the title maintainer. I never liked it because it sounds as if the maintainers are the car mechanics that get their hands dirty and everybody else is a passenger and lets themselves drive around. And that's really not it. I think instead of maintainer, it should be called editor. Books are edited, journal articles are edited. And the editors do an important amount of work. And sometimes they look at articles and review them, I mean, particular for Nature papers, but not all the time. There's a lot of work that comes from other people. And in principle, it should be most of the work. Sorry, noise here.
That's okay. Many of us have children. Yes, no, Eric.
I got my point across, and I want to push for calling us editors instead of maintainers. I mean, with an explanation, but maintainers can too easily be misunderstood. I know there's a grad student and they're a maintainer of the Einstein toolkit. That really doesn't look good on their CV. But if there's a postdoc and they're editor of a large software package that's been around for a decade, that carries some weight.
That's interesting. I hadn't thought of it in terms of how that looks. Unfortunately, research software engineering isn't as widely recognized as a field as it should be. So editor probably would carry more weight. I hadn't thought of that. All right. We have 5 minutes to 12, so we've got 5 minutes left in the schedule for the day. I'm looking for any closing thoughts any of you might want to share with our assembled workshop participants on the Einstein Toolkit, its future, its value, so on. So just at one, yes, we have Yuan Chuan Zhu. What would you like to say?
Yes, here I am. I'm originally from China, and you may see some Chinese names from the participants here. And they are actually right now in the midnight and attending this kind of workshop. And yeah, my thing is it possible to expand the community to the east of the Earth, and maybe sometime later you can hold a kind of workshop in the China's time, and maybe after the COVID-19 can go to China and make some kind of advertisement or spreading. And there will be many students and staff, faculties are very interested in the Einstein Toolkit.
That's a cool idea. Just shift the time zone. Yes, I mean, if we want to do it soon.
Yeah. So I picked these times because it worked for Europe and the U.S. Obviously, I can't pick something that works for the whole globe, but China is. It would be nice to. Well, okay. So we did do a workshop for the Einstein Toolkit in China back in 2013. Maybe you missed it.
Yeah,
But I would certainly be welcome. I would certainly be interested in trying to put something together, and even if maybe it's only something that's timed better for China, and it's virtual. But yes, we would definitely like to see more contributions from China.
Yeah.
Thank you.
Yeah, or not China, because there's actually someone in the chat who Jay pointed out there's also India. So essentially, on the eastern side of the globe. And I think that's a great idea because the idea is to build a community and to be inclusive.
I guess instead of thank you, Yuan, I should have said shishi.
Yeah, I recognize. Thank you. Thank you.
All right. Anybody else have any closing thoughts?
Yes, Steve, just related to the previous comment, Yuan Chan. So if everything works out with the COVID situation, et cetera, I hope to be living in China for a year, starting a year from now. So I'd be happy to, help in whatever way I can when I'm there. I'll be in Hefei or Hangzhou when I'm there. So that's kind of centrally located. So, and certainly accessible through the bullet trains. So it might be an idea to organize. So if you're interested, and of course, if things work out, fingers crossed, I would be interested in, I'd be happy to help out.
Yeah, thank
I'm
you.
looking forward to seeing the workshop you organize in China.
I didn't offer to organize it. I just said I'd be happy.
Oh,
to
okay.
I don't think I have the appropriate amount of guanxi if the Chinese attendees here understand what I'm saying.
Well, maybe you can figure out a way to make something like that happen while you're there. That would be nice. All right. It is noon. That's it for today. I thank you all for attending. As far as lightning talks, which is a small way to contribute just to this workshop, those are still available, and you can sign up for that. I will be sending out an email again. But you can use the same links from yesterday's email to see the video after it's post-processed. Very slightly post-processed. The post-processing is going to take place over the next week, and we'll break it up into individual talks, and we'll have an entire virtual online workshop. But anyway, thank you for attending, and thank all our speakers and everyone. We look forward to seeing you tomorrow.
See you. Bye-bye.
Thanks, everybody.
Bye-bye.
Bye.
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 Bye-bye.